Hello, class. This recorded lecture for section 6.8, which again is application of models of exponential functions. And we're going to focus on two of the four in this chapter. We're going to do uninhibited growth and decay modeling and calculations. And so when you take a look at this equation that we're going to introduce, it's going to look exactly like the equation in the last section where we were dealing with compounding interest, but compounding continuously. So again, these are based on the exponential function with the base e in it, the natural base. And again, this shows up in the real world modeling a lot. And so we'll walk through one example for growth and one example for decay. Before we get started, let me show you a couple of these graphs here and give you a feel for what we're going to be doing here. So there are the growth, which is on the left side. As you can see, the slope is positive. And then on the right side is decay. The slope is negative. And if you could see these equations here, it's we're using the letter A, but basically you could think about that as the amount, right? And so the amount at time t, and then this A0 is basically the initial start point. And so, and then E is our base, and then K is like the interest rate, right? So K is going to be our, they call it growth rate. And if the growth rate is positive, if K is positive, excuse me, then the growth rate is increasing, right? And we call that growth. And if K is negative, you could see this is decreasing, right? We call that decay. And so the equations are exactly the same. The only difference is the K value is going to be positive for growth and negative for decay. And so let's take a look at an example. And so I like this example here, this idea of bacterial growth. And so what we're going to do is we're going to set this up where a colony of bacteria increase according to the law of uninhibited growth. And they're using the letter N. We could use A. So I'm going to use N because that's what's in this problem here. But if N is the number of cells and T is the time in hours, and express N as a function of T. So again, just keep these equations handy. You don't have to memorize anything, but this is the growth equation. And decay, right? It would be N of T equals initial condition N0, E, and then to the KT. And so T is in hours. And so it's a little bit different than the money problems, right? With regards to compounding interest, where T was always in years. Here, it could depend on how fast things grow and how fast things decay. So, but T is always time. And so K is our growth, right? And N0 is the initial condition. And so that is, I believe, the answer to question number A, or letter number A. And so the next question says, if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in this culture. So this is very similar to what? When we were calculating the value or the time it took to double your money, right? And so if we take a look at this equation again, it takes T equals 3 hours to double, right? So how would you think about what a double? Well, if we start n0, what happens when it doubles? It would be 2 times n0, right? So when we set up the equation, it would be 2 times n0 equals n0 e to the k, and we'll plug in 3 hours. So now we're finding the growth rate, right? And we'll just put it right there. So the idea is that we can solve this equation by doing the following. You could see that these would cancel, and you would have 2 equals e, and we have 3k up here, right? So what do? Well, here's where the log function becomes quite handy. As I warned you, this is what logs are really for. If we take the log of both sides, we'd have natural log of 2 equals natural log of e to the 3k. And now use the power rule property of logs, right? Natural log of 2 equals 3k, natural log of e. And that's why we took the natural log to make the arithmetic a little bit easier, right? Because natural log of 3 equals 1. I'm sorry, natural log of e equals 1. And so if we divide each side by 3, what does k equal? Natural log of 2 divided by 3. So you have to get out your calculator, right? And if you did that, you would get 0.23105. And there's always this question about how many decimals should you do with regards to these calculations. Obviously, the more you put in there, the more accurate it's going to be. And it just depends on the value of it. In this case, 5 would be plenty, especially if you look at this because of this 0 here. You could actually round it to 3 decimal places and you would get a very accurate answer. I just did 5 because that's what the book did. So now what is our equation? Well, now we know our equation because we know k, right? So again, it's n0 e to, and you see it's positive 0.23105 t. So if you looked at the list of those 4 problems, that was problem B. So let's take a look at what problem C states. So then it says, how long will it take for the size of the colony to triple? Okay, so if you go back to our equation, what do we need to do here? So now we need, I don't want to clear all this, but let me erase this here, all right? So now we want to do what? Triple, right? So we know what k is. We still don't know the initial condition yet, but typically you'll be given that if you're given a problem where you have to calculate a value. And so in this case, we want to triple, right? So what value of t for triple? So again, if we start with n0, what would tripling be? All right, it would be 3 times n0. So again, you probably see this pattern here. So now we'll have a very similar equation, but now we know what k is. So let's put k in, and now we're going to calculate t. So again, n0 cancels. And you could see we have, whoops, what am I doing here? Forgot my equal sign. 3 equals e to the 0.23105 times t. So I think you see the pattern, and you're going to do this quite a bit in this last section and now this one, where you take the log of both sides, so we could use the power rule. And so if we go back up here, we use the power rule for logs now, and we can bring the exponent down to 23105 times t. Natural log of e, that goes to 1. And so you have natural log of 3 equals 0.23105 t. And so t would equal natural log of 3 divided by 0.23105. And if you got your calculator and did that one, it looks like it'd be approximately 4.755 hours. Again, that's what we have in the book. And so if you remember from the first problem, it took how long to double? It was 3 hours, right? So how long to triple? Well, you knew it had to be greater than 3 hours, right? And so you think about that, it kind of makes sense, right? And so the last problem that we're going to do in this one is here we don't even have to get our calculator out for the last one. We just need to think a little bit. And I like this last one because it makes you think. So how long will it take for the population to double a second time? That is the increase by a factor of 4. Well, you can walk through the analysis and you're going to get an answer of 6 hours. And why is that the case? Well, look what happened here, what we were given, right? So it doubles in 3 hours. And that's what exponential is all about. So it's going to double again in another 3 hours and double again in another 3 hours. So when we talk about growth and why exponential functions grow so fast, it always follows that pattern. So here you really don't even need to do a calculation. It would be, 6 hours. Just like if I asked you, how long would it take for the bacteria to increase by a factor of 6, right? Well, we calculated how long it would take to triple. So how long would it take to do that again with regards to that calculation? Let's take a look at that real quick. And so if we did that one, right, we're going to do a factor of 6. And I want to point this out because this is a typical mistake sometimes people make. Because look what will happen. And so instead of doing this, we're going to do 6 times, right? And so that would be 6 and 0 e to the 0.23105t. I forgot my n0 there. So you could see the pattern, right? So now we have 6 over here. E to the 0.23105t. And so take the natural log of both sides, you get natural log of 6 equals natural log of e 3105t. Use the power rule. Natural log of e goes to 1. And so t equals natural log of 6 over 0.23105. And so let me get my calculator out, and you would get 6 natural log, and then you divide by 0.23105. And you could see it's 7.754 hours. And if you remember our initial calculation for 3 was 4.755 hours. So you see it's not double. And what we mean by that is that if you're looking for taking this number and doubling it, that means that you're going to not do 6 times, but 9 times. And that would be 3 times 3. And so if you walk through this analysis, and again, instead of having 6 times, we did 9 times, right? What's the only number that changes? And you see the pattern now? That's why I like to point this out. So if you see this pattern now, you're going to have a 9 here, 9 here, 9 here, 9 here, and 9 here. And so if you do this one in green, 9 natural log, and you divide by 0.23105. Oops. You see, this ends up being 9.5097, which is twice this value. So this is the 9 times, and this is the 6 times. So you see what we mean by exponential, right? 2 is nice because 2 squared is 4, or 2 times 2 is 4. But 3 is not, right? So 3 times 2 is 6, and you're not doing it 6 times, right? With regard to that, if you want to actually that to go up by twice the time, it would be 3 times 3, or 9 times that number. So that's going to end the first of the 2 recorded lectures for this section. This one was on exponential growth, and the next one will be on exponential decay.